Good morning, everyone. This is the report of Group 3 in Hydrology. Our report is all about interception. Concept Module Map, Interception, Introduction and Definition, Interception and the Water Balance, Measuring Interception, Factors affecting interception loss from vegetation, interception losses from different types of vegetation, cloud water deposition, interception of snow.
Great. This is about interception. Interception is a very important part of the surface water cycle. Super. So the reason why I'm making this presentation is because in the timed pressured situation of the exam, candidates sometimes confuse interception with infiltration. So when you've watched this, you won't ever do that again. These are the three questions that I'm going to take you through. Interception is defined as the storage of water in or on vegetation before it reaches the ground surface. So here we have a leaf, it's rained on the leaf, and water droplets have formed on the surface of the leaf, and they're being held there by the leaf. The amount of interception will depend on the shape of the leaf. It will depend on the form of the leaf. You can see here this leaf has got specific runnels in it where the water could be stored, whereas this one from an older tree is relatively flat. All kinds of vegetation will intercept some water, but trees are the most effective interceptors, and this depends on their density. So if we look at this coniferous tree, like a Christmas tree, one which is evergreen all year round, it is able to intercept around 25% to 35% of all rain in a year. By contrast, deciduous trees like this one, which lose their leaves in autumn, here you can see the leaves have gone red, they're going to fall off, they will only intercept between 15 and 25% of annual precipitation. And so the type of the tree, the density of the canopy, and obviously the density of the trees in a plantation, in a forest, is going to affect how much water is intercepted by that tree. The duration and the type of precipitation that fall also have an impact. So let's imagine it starts to rain in this forest. The leaves start to collect water. As the rain proceeds, more water is added to the leaf. At a certain point, that leaf becomes too heavy, and all of a sudden, the leaf will suddenly droop, and then we get leaf drip. The process of leaf drip will empty the interception store. So if it's only a light rain shower, interception can be close to 60 or 70% of that rain shower. But if the precipitation intensity and duration is long and intense, then we will get less interception because it will then follow the pathway of leaf drip or even stem flow and will reach the ground surface. Secondly, in boreal forests, like those in Siberia in the northern hemisphere, a substantial amount of precipitation falls as snow. During the winter, the snowfall accumulates on the branches of the tree, and the trees are structured in such a way that they actually catch a huge amount of that snow. It's estimated that between 10 and 20 kilograms of snow can be stored in the branches of these trees per metre squared of forest. So this is very important, and it means that the precipitation is stored, and then in spring it's suddenly released in the spring snow melt, which has an impact on the river levels and on the rest of the catchment's hydrology where the trees are. Interception loss is the process by which a droplet of water which has landed on the leaf then goes back into the atmosphere again via the process of evaporation. This is controlled by temperature. Higher temperatures, more evaporation. It's also controlled by wind speed, higher wind speed, more evaporation, more loss of water from the interception store. And thirdly, it's controlled by humidity, because in conditions of high humidity, the evaporation rate is lower. Human activity affects interception in a number of ways, and you can probably think of lots of these, but here's two. Number one is deforestation. If the forest cover is lost, obviously there's going to be no foliage to catch in the incoming precipitation. Therefore, we see more surface runoff. More surface runoff leads to increased water in the river channel, leads to increased risk of flooding, like we've seen in the tropical forests and the Madeira Basin in the Amazon. Secondly, many areas of forest have been turned over for agriculture. For example, here we have one of the world's most used products in food, the soya bean. When the soya bean is planted, obviously it's able to intercept incoming precipitation. But when it's harvested, then there's no interception whatsoever. So when cereal crops of all kinds are harvested, this means that the sunlight then reaches the ground surface, and that can lead to baking effects, then reducing infiltration, which we'll look at in a later presentation. One of the fruits which is really, really well liked in my household is the mango. Here's a picture of a mango tree, here's a picture of an unripe fruit, and here's a picture of a mango which is ready to eat. Let's look at the data on the mango tree. These two graphs are taken from some really recent research done in 2018 on the mango tree. So the mango tree was involved in two precipitation events, Event 1 and Event 2. Study these graphs, and then I'd like you to suggest reasons why the blue line, the interception, in this tree were different for the two different events, rainfall events. Rainfall is shown in red. Press pause now, have a think about this before you move on. So a couple of things to notice here. On the y-axis we've got two different scales. In Event 1, around 30 millimetres of rain fell. In Event 2, however, around 79 millimetres of rain fell. And we can see that Event 2, there's a much bigger gap between the amount of rain that falls and the amount of rain that can be intercepted. So we're going to assume that where this occurs, where this level flattens out here for the interception, we were assuming there that probably that's because the interception stores on the mango tree, every leaf is full. So at this point, after this point, we're expecting that leaf drip processes and stem flow processes will be more important. You will have noticed that the red line showing the rainfall shows a different pathway. Here the onset of rain is low and the amount of rain is also low. And so most of the graph of interception tracks alongside the rainfall, and the mango tree is able to absorb almost all of the rainfall storm in this case. However, when the rain is more intense, the tree, there's a bigger gap here between interception and precipitation, and the reason for that is because a lot of the rain is running off the tree, it's running down the stem, and it's been involved in leaf drip processes. In summary, interception is affected by wind, humidity and precipitation. Coniferous trees like this one, evergreen trees, are better at intercepting rainfall than deciduous trees. Complex stratified forests like the tropical rainforests are much better at intercepting rain than soya plantations or palm oil plantations. And human activity reduces interception. Urbanisation, farming and deforestation will all have this effect.
Lesson 1. Introduction and Definition. Interception refers to precipitation that does not reach the soil, but is instead intercepted by the leaves, branches of plants, and the forest floor. It occurs in the canopy and in the forest floor or litter layer. Because of evaporation, interception of liquid water generally leads to loss of that precipitation for the drainage basin, except for cases such as fog interception dramatically. Intercepted snowfall does not result in any notable amount of evaporation, and most of the snow falls off the tree by the wind or melts. However, intercepted snow can more easily drift with the wind out of the watershed. Conifers have a greater interception capacity than hardwoods. Their needles gives them more surface area for droplets to adhere to, and they have foliage in spring and fall. Therefore, interception also depends on the type of vegetation in a wooded area. Lesson 2. Interception and the water balance. When precipitation reaches the surface in vegetated areas, a certain percentage of it is retained on or intercepted by the vegetation. Rainfall that is not intercepted is referred to as true fall. Water that reaches the ground via the trunks and stems of the vegetation is called stem flow. The interception storage capacities of the vegetation vary with the type and structure of the vegetation and with the meteorologic factors. Measurements have shown that up to 8 millimeters of rainfall can be intercepted by some vegetation canopies. The intercepted water is evaporated back into the atmosphere at rates determined by the prevailing meteorologic conditions and the nature of the vegetation. In humid temperature areas, evaporation of intercepted water can be an important component of the water balance. Forest areas have been shown to have greater interception losses than adjacent grassland areas. This is due to the greater aerodynamic roughness of the forest canopy, resulting in a much more efficient transfer of water vapor away from the surface. Stem flow. Stem flow is the flow of intercepted water down the trunk or stem of a plant. Stem flow, along with through fall, is responsible for the transferal of precipitation and nutrients from the canopy to the soil. In tropical rainforest, where this kind of flow can be substantial, erosion gullies can form at the base of the trunk. However, in more temperate climates, stem flow levels are low and have little erosional power. Infiltration. Infiltration is the process by which water on the ground surface enters the soil. It is commonly used in both hydrology and soil science. The infiltration capacity is defined as the maximum rate of infiltration. It is most often measured in meters per day, but can also be measured in other units of distance over time if necessary. The infiltration capacity decreases as the soil moisture content of soil's surface layers increases. If the precipitation rate exceeds the infiltration rate, runoff will usually occur unless there is some physical barrier. True fall. True fall is the process which describes how wet leaves shed excess water into the ground surface. These drops have greater erosive power because they are heavier than raindrops. Furthermore, where there is a high canopy, falling drops may reach terminal velocity about 8 meters or 26 feet, thus maximizing the drop's erosive potential. Rates of true fall are higher in areas of the forest where the leaves are broad-leaved. This is because the flat leaves allow water to collect. Drip tips also facilitate true fall. Rates of true fall are lower in coniferous forest, as conifers can only hold individual droplets of water on their needles. True fall is a crucial process when designing pesticides for foliar application, since it will condition their washing and the fate of potential pollutants in the environment. Canopy interception. Canopy interception is the rainfall that is intercepted by the canopy of a tree and successively evaporates from the leaves. Precipitation that is not intercepted will fall as true fall or stem flow on the forest floor. Forest floor interception. Forest floor interception is the part of the net precipitation or true fall that is temporarily stored in the top layer of the forest floor. and successively evaporated within a few hours or days during and after the rainfall event. The forest floor can consist of bare soil, short vegetation like grasses, mosses, creeping vegetation, etc., or litter, leaves, twigs, or small branches. Lesson 3. Measuring interception. Interception is most easily measured by comparing rainfall underneath vegetation cover, like a woodland canopy, with rainfall where there is no vegetation cover. Place several identical rain gauges in the contrasting areas. Don't just use one rain gauge per area. You can construct a simple rain gauge from an empty plastic bottle. 2-liter size works well. Remove the lid, then cut off the top third of the bottle. Invert this top section into the bottom part. Dig a hole and bury the rain gauge so that about 5 cm is sticking out of the ground. Leave the rain gauge in place for a few days when rain is forecast. Measure the amount of rain collected in each gauge at the same time each day. You could either measure the depth of water in the gauge or pour the water into a measuring cylinder to measure the volume. Alternatively, you can compare interception beneath and beyond an individual tree during a single rainstorm by placing several rain gauges at increasing distance from the tree trunk. Measure the depth of water in each gauge every 15 minutes during and for some time after the rainstorm. The stem flow and drip will continue after the rain has finished. Interception by buildings can be assessed by measuring the volume of water discharged by all external guttering and drainage pipes. You may wish to use interception measurements for one tree to calculate the interception caused by an area of woodland. The simplest way to do this would be to estimate the number of trees in the woodland and multiply accordingly. Or you could measure the size of the tree canopy and then multiply up to the size of the woodland. Stem flow measurements. The stem flow is most easily measured for a single tree. Choose a tree with a single large trunk, at least 50 cm trunk circumference at shoulder height. Rub split plastic tubing to encircle the tree trunk. 25 mm diameter PVC tube is suitable. Cut in half lengthways. Use a wire brush to remove moss from the trunk before installing the tube, so that moss does not fall into and block the tube later. If you are comparing several trees, position the tubing at a consistent height of the ground, starting at shoulder height and wrapping at least twice around the trunk is practical, as you will be able to install tubing without needing a ladder. Use silicone sealant to make a seamless seal between the trunk and the gutter. Direct the base of the tubing into a collecting vessel, such as a large sealed bucket. Leave the tubing in place for a few days when rain is forecast. Measure the amount of rain collected in each collecting vessel at the same time each day. You could either measure the depth of water in the gauge or pour the water into a measuring cylinder to measure the volume.
My name is Jesper Riis Christiansen. I'm an associate professor at the Department of Geoscience and Natural Resource Management at University of Copenhagen. We are here in Vestskoven where we study the process of how much rain that is caught by trees before it enters the ground in our new project called Interception. This naturally has an impact on how much water there's in the soil and eventually can end up in the groundwater as our drinking water resource. What we are hoping to achieve here in interception is to derive some fundamental relationships between the structure of the vegetation and the water dynamics, measured at scales that we before have not been able to measure at. We are trying in interception to study this in a new way, because the numbers of how much rain is caught in the trees are surprisingly difficult to determine accurately. So in this project we are trying with new types of measurements to measure this directly for the whole forest. Because if we look around in this forest, we see there's so much variation. So many different trees, they are different heights. Some places there is no trees, some places there are trees, so there's a lot of variation. We need to capture this variation, and that's what we're trying to do in this project. So to achieve this measurement of interception in this forest, we combine different techniques. So the first one is very simple. We simply collect how much rain or water is dripping below the canopy. But in order to calculate the interception, we also need to measure it outside the forest. The difference between these two measurements is the interception. Another interesting instrument we're using are actually artificial leaves. Artificial leaves are able to measure how wet they are, and that's important to understand when we have a rain event happening in the forest. They can measure how fast the canopy gets wet. By having these measurements and the rain gauges, we can relate the intensity of the rain, how much it rains per hour for example, to how fast the canopy is re-wetted. It can also tell us the dynamics between when we have no leaves on the trees and leaves on during the summer, because we think there are a difference in the interception in these two periods. So the instrument behind me is called Cosmic Ray Neutron Detection, and my colleagues in the project interception at Geology, they are working on trying to understand how to use this equipment to measure the water dynamics for the whole forest. So to link the cosmic ray methods and the rain gauge method and artificial leaves, we are also using LiDAR, a laser technique that can measure the forest structure. So LiDAR is basically a very advanced 3D ruler. It can measure distances in all directions and do that in real time. The cool thing about the instrument we have here is that it's not stationary. We can walk through the forest with our LiDAR instrument and then at the same time measure the structure for the forest. The 3D geometry of the forest can be linked up to measurements of geometry of the forest, for example from satellites or planes. This is a very cool way of scaling our measurements from the forest plot to maybe larger scales across Zealand, across Denmark. So basically the methods we are using has relevance for studies of water resource dynamics across the world. That could be in agricultural systems, in savanna systems, rainforests, basically anywhere where we are depending on the available water resource for either our economy or our agriculture or livelihoods or the nature.
Lesson 4. Factors affecting interception loss from vegetation. Interception loss is that proportion of the precipitation which is returned to the atmosphere through evaporation from plant surfaces or is absorbed into the plant. Thus, it is the difference between the precipitation actually occurring over an area and that which reaches the ground. Interception deals with the amount of water that is caught and stored on the leaves and stems of vegetation. The term vegetation includes forest tree cover, crops, and low-level vegetation like underbrush, grass, and etc. Part of the precipitation, which falls either as rainfall or snowfall, is caught by vegetative cover before it reaches ground. This is a matter of common experience when the people take shelter below a tree during rainfall. The tree drops or snowflakes are retained by the leaves as droplets or thin layer on their surface or in the depression of the leaves. After this storage capacity is exhausted and the rain or snow starts dripping down, some water also flows down along the stems of the tree or the plant. The rate of interception is high at the beginning of the rain in case of a dense vegetal canopy during summer. As time progresses, and if the storm continues, the rain starts falling through the tree canopy. Factors affecting interception. The amount of the amount of water intercepted is greatly variable and depends on many things. Since the interception affects the distribution of rainfall or snowfall and subsequent runoff, it is necessary to understand the factors which affect interception. Type of vegetation. Interception varies with the species, its age and density of stands. About 10 to 20% of precipitation occurring in the growing season is intercepted. It is lost substantially by way of evaporation from leaves. In dense tall vegetation, interception is quite substantial, so interception by low-lying vegetation is usually negligible for hydrologic studies. But if such vegetation cover exists below the forest canopy, it affects runoff substantially. Dense grasses and herbs approaching full growth intercepts as much precipitation as forest cover. However, since their season is short, total amount intercepted is considerably less than the forest cover. Wind velocity. If the wind accompanies the precipitation, the leaves become incapable of holding much water as compared with the still air condition. On the other hand, due to blowing of wind, the evaporation rate also increases. It is thus seen that during short storm interception decreases, but during long storm interception is augmented due to increased evaporation. Duration of storm. Interception storage is filled up in the first part of a rainstorm. Therefore, if yearly precipitation is made up of several small duration storms separated by dry spells, evaporation will be high and interception will be consequently more. However, if storms of long duration occur and if weather remains cloudy, relatively interception loss will be less. Intensity of storm. When precipitation occurs in still air conditions with low intensity, interception will be more. On the contrary, if raindrops come with great speed, their impact dislodge intercepted drops and leaves cannot hold much water. Season of the year. During summer or dry season, the interception rate is quite high because of high evaporation. Summer interception is 2 to 3 times more than the winter season interception. Climate of the area. In arid and semi-arid regions, due to prevailing dry conditions, the interception loss is more than that occurring in humid regions. Lesson 5. Interception losses from different types of vegetation. Vegetation characteristics. Interception increases exponentially during a storm until the interception capacity is achieved and the weight of more rain overcomes the surface tension holding the water on the plants. Also, snow periodically slopes off plants when the capacity to intercept snow is achieved. Interception capacity is a function of growth form, trees, shrubs, grasses, forbs. Coniferous trees intercept 25 to 35% of annual precipitation. Deciduous trees intercept 15% to 25% of annual precipitation, but just as much as coniferous trees during the growing season. Trees also have greater interception capacity because they project above ground and into the wind, creating turbulence which drives water on the lee side and into the interior of the tree. Grasses and forbs have high interception capacity during the growing, but then either die, annual plants, or lose mass, perennial plants. Also, they are grazed and harvested. Spring wheat intercepts 11 to 19% of precipitation before harvest. Plant density, biomass data, mass per unit area, are poor indication of interception capacity. Rather, the extent of ground cover and canopy closure are the important aspect of density. Plant structure, number, size, flexibility, strength, and patterns of branches, texture, surface area, and orientation of leaves. Trees native to regions of heavy snowfall have flexible branches and trunks to support and shed heavy snow loads, 10 to 20 kg per meter squared for wet snow. Thus, forest mensuration data, trees' heights, diameters, and volumes, are a poor indication of interception capacity since they don't convey tree structure. 4. Plant community structure. Secondary interception occurs in stratified forest communities, where water drips from the canopy and is intercepted by lower plants. In short vegetation, interception storage merges with surface storage, especially if the plants are flexible and bed under the weight of water. Lodgings of crops, which can substantially reduce yields. Snow cover on scrubby vegetation and tall grasses is very irregular with large void spaces representing up to 40% of the snowpack. Hydrological properties of an area have been changed by the process of urbanization, which results especially in increased runoff. Previous studies have suggested that rainfall interception by urban trees can reduce the runoff. The amount of intercepted rainfall depends on type of vegetation and on meteorological conditions, which have the impact on reduction and retention of runoff, which is important in urban areas. Performance. Zabret and Esraj 2014. From 1st of April to 31st of July 2014, had measured true fall and stem flow under two deciduous trees, Betula pendula, and two coniferous trees, Pinus sylvestris, in centers of Ljubljana, capital of Slovenia. Under each type of tree, true fall was measured with two throw gauges, one equipped with tipping bucket and one with manual 60 tank to control automatically gathered data. There were also 10 manual roving gauges, which were randomly moved under the tree canopy. The stem flow was measured on one tree of each type, with rubber collar fitted around the tree. The tube was connected to manually reading 20 plastic tanks. Data were collected after each event. Gross rainfall was measured using a tipping bucket rain gauge located on the clearing near the trees. During the measuring period, they have detected 85 rainfall events with total depth of 488 mm. The average amount of gross precipitation per event was 57 mm and range from 0 2 mm to 57 mm. True fall events measured automatically with tipping bucket were grouped according to the dates of manually collected data and verified with weight average of data collected with throw gauge and roving gauges. Cumulative true fall for Birch Betula pendula was 285 mm with average value of 6 mm per event and standard deviation of 731. True fall amount measured underneath pine. Venus sylvestris was 209 mm with an average value of 34 mm and standard deviation of 562. The total amount of stem flow or birch was 1162 mm and for pine 072 mm. In case of birch, stem flow was generated when the total rainfall exceeds 48 mm, while the threshold depth of total rainfall for generating the stem flow on pine was 5 and 8 mm. Birch and pine have intercepted 40.2% and 58.3% of rainfall, respectively. The interception value suggests that coniferous trees, in comparison with deciduous trees, intercept more rainfall, not only in winter time, when deciduous trees are leafless, but also in spring and in summertime. Possible parameters contributing to that are vegetative properties of coniferous trees, which are thicker tree canopy, rougher bark, and the slope of the branches away from the tree trunk. As a result of those properties, stem flow was much lower for pine in comparison with birch and can be even neglected. This figure represents the different types of coniferous trees and deciduous trees. Lesson 6. Interception of snow. If you walk through the forest on a rainy day and notice that it's drier under the trees, you've experienced interception. In hydrology, interception is when water gets hung up on vegetative leaves, needles, or branches and never makes it to the ground. The precipitation gets evaporized if liquid or sublimated if solid back into water vapor directly from the vegetative surface before it gets a high chance to hit the ground and infiltrate or run off. If the water hangs out in the vegetation for a while but eventually makes it to the ground, we call it stem flow or true fall, depending on whether it ran down the tree trunk or not. Interception can be a pretty significant component of the water budget. In forests, the vegetation can intercept 20 to 40+% of precipitation. In grassland, the numbers are in the 10 to 20% range. Even litter, the dead plant material covering the soil, can cause interception. Interception rates depends on plant type and density, but also how much rain you get, how fast it falls, and how much evaporation can occur during and between storms. In the winter, interception still happens during snowfall, but now vegetation type really matters. Since deciduous trees shed their leaves in the winter, they become pretty useless for interception. In the feature, you can't really see the difference between the deciduous forest and the lawn. They are both fully snow-covered. On the other hand, since conifers retain their needles, they can capture a lot of snow. And you can see that in the bare ground under the trees at left. Whether the conifers truly intercept all that snow is more complicated. Conifers can initially hold large snow loads, but wind can blow that snow onto the ground. It can be dumped off in large clumps, and melting within the snowpack on the branches can allow the water to drip to the ground. In order to effectively intercept the water and return it to the atmosphere, we need sublimation to happen faster than those other processes. Lesson 7. Cloud water deposition. Clouds are created when water vapor, an invisible gas, turns into liquid water droplets. These water droplets form on tiny particles like dust that are floating in the air. Liquid water changes into gas when water molecules get extra energy from a heat source such as the sun from the other water molecules running into them. These energetic molecules then escape from the liquid water in the form of gas. In the process of changing from liquid to gas, the molecules absorb heat, which they carry with them into the atmosphere. That cools the water they leave behind. This figure shows that heat causes some of the liquid water from places like oceans, rivers, and swimming pools to change into an invincible gas called water vapor. This process is called evaporation, and it starts of how clouds are formed. The air can only hold a certain amount of water vapor, depending on the temperature and weight of the air, or atmospheric pressure, in a given area. The higher the temperature or atmospheric pressure, the more water vapors the air can hold. When a certain volume of air is holding all the water vapor it can hold, it is said to be saturated. What happens if a saturated volume of air cools or the atmospheric pressure drops? The air is no longer available to hold all that water vapor. The excess amount changes from a gas into a liquid or solid ice. The process of water changing from a gas to a liquid is called condensation, and when gas changes directly into a solid, it is called deposition. These two processes are how clouds form. Condensation happens with the help of tiny particles floating around in the air, such as dust, salt, crystals from sea spray, bacteria, or even ash from volcanoes. Those particles provide surface on which water vapor can change into liquid droplets or ice crystals. A large accumulation of such droplets or ice crystals is a cloud. This figure represents the dust and other particles floating in the air provide surface for water vapor to turn into water drops or ice crystals. The tiny drops of water condense on the particles to form clouds droplets. Clouds are made up of a bunch of cloud droplets bundled together with raindrops. We usually think of clouds as being up in the sky, but when conditions are right, a cloud can form at ground level too. Then it's called fog. If you ever walk through fog, you walk through a cloud. Although the basic idea of cloud formation is easy to understand, there is much more to learn. Peek beneath a cloud's fluffy exteriors and you'll find a world of complexity. In fact, clouds are considered one of the most challenging aspects of climate science. That's because truly understanding clouds requires a deep understanding of the entire atmosphere. Scientists are working to increase their understanding with the help of instruments such as those on NASA, Terra, Aqua, Aura, Calypso, CloudSat, and other satellites that observe different aspects of clouds. The better, the better we can understand clouds and the atmosphere that creates them, the better we can find out what's happening to our climate. That's the end of our reporting. Thank you for listening.